In this video, we're going to explore how we can define the dimension of a vector space and how that ties back to the concept of a basis. So the definition is fortunately very simple. The dimension of a vector space V, which we write as dim V, is simply the number of vectors in a basis for that vector space. Now note that it is possible for a vector space to not have a finite basis, in which case we say the dimension is infinite. In other words, it takes an infinite number of building block vectors to span that space. Now there's some pretty simple examples. If we have R, that is a vector space with one dimension, sort of implied by what we know about it. We're going to prove this a little more rigorously soon, but guess what? R2 is two-dimensional, R3 is three-dimensional, and so on. Those are the obvious n-component vector dimensions, but we can also get a set like P2, which is equal to the span of a constant, an x function, and an x squared, so the second degree polynomials, and so that would be a three-dimensional space. In terms of infinite dimensions, that would be something like C infinity. We'll look at this in more detail later, but the fact that we can't represent a polynomial, a finite dimensional polynomial, as all C infinity functions like e to the x, sine of x, those kinds of functions, that leads us to believe that we're not going to be able to cover this space or build this space just with a finite number of building blocks. So C infinity would be one of those cases. Now, because we're working in a proof-based class, we actually need to confirm that whenever we pick any two bases for the same vector space, we actually get the same number of vectors. So if we go back a second here, there's an assumption built in that we didn't talk about. The dimension is the number of vectors in a basis for V, and we're worried about maybe there's a loophole where I find three vectors somehow that are a spanning set and linearly independent in R2, and you only find two. How do we reconcile that? What we're going to need to prove is that no matter what basis anybody finds, there are always going to be the same number of elements in it. We're going to do that with the help of what's called a lemma. So from Wikipedia, a lemma is generally a minor proven proposition, which is a stepping stone to a larger result. So it's like a theorem, something that can be proven, but it's generally not considered as fundamental or as foundational as a theorem. So it's often called a lemma or an auxiliary theorem or a helping theorem. So the key lemma we're going to be using is, assume we have a vector space, and we're going to talk about two sets of vectors here. One u, one to ua, and that set is linearly independent, and a second set that is a spanning set. And you can see how we might hone in on the idea of a basis here by comparing and contrasting these two kinds of sets. The theorem, or the lemma here, specifically states that if we have these two sets, then the number of elements in the first set, the linear independent set, has to be smaller than or equal to the number of elements in the spanning set of V. So one quick way to visualize that is we have our u's here. We have u1, u2, all the way down to ua. They're hanging out in some space, and a is the number of those vectors. Meanwhile, we have a potentially bigger set over here where we have v1, v2, and a bunch of other points down to vb, and this has b as the number of vectors. And the claim of this theorem is that the a value is less than b, or this set is smaller than or equal to the size of this set here in terms of numbers of elements. They can be totally different vectors, that's totally fine, but the number of them is going to be that this is always smaller, with that condition that these are linearly independent, while these ones over here are a spanning set. Let's make this a little concrete by going back to our R2 examples and playing with that idea. So if we have a linearly independent set in R2, well, one way to get that is to simply have just a single vector, right? A single vector, that's a equals 1, that's a linear independent set. And I'm going to bring a few things in here. Let's imagine linearly independent. We could also have two vectors in there, like so and like so. That could be u1 and u2. That would be a equals 2. And how else can we build vectors? Well, I could have three vectors, so we can just imagine different sizes of sets. So ua, u1, u2, u3. However, if we take a look at this, there's a bit of a problem, right? these three vectors are not linearly independent. So not linearly independent at three vectors. And so we get this idea that in R2, again, this is intuition, not a proof yet, but we get an idea that the biggest number of vectors we're going to have that are linearly independent is going to be 2. Okay, well, let's talk about generating sets. Let's start at the bottom and work our way back up. So if we have 3 vectors here, that would be v1. Let's pick different looking vectors so we're not accidentally including the same one. So v1, v2, v3. This absolutely is a generating set, and the number of elements in it is 3. And we could have 2 vectors like so, v1, v2, and that would have 2 elements in it, so v equals 2. And then if we go to, a single element, so let's call that v1. So that's our b equals 1 case, but wait a minute, I'm trying to get to all the points in R2. This is not a generating set. Cross that off. So for linear independence, fewer vectors is fine up to it feels like some threshold. For generating sets, large is fine, and we can get it smaller and smaller until some threshold, and then we stop having a generating set. And so we have this idea that linear independence compared to the size of a set that's a spanning set, we're going to have this tension. These sets are largely bigger, spanning sets tend to be bigger, and the linear independent sets have to have some limited size to them. Now again, proving that this strict matchup is true, the fact that we have an alignment where linear independence maxes out is exactly the same point where generating sets minimize out. That takes a little more work, but that's the idea that we're aiming for here. Now that key lemma can be proven in several ways, and if you'd like the PDF for that, I'm happy to provide it. It's based on the work of another professor, Michael Roth. It's not the most instructive proof for what we need it for, but it's a good exploration of ways we can use systems of equations and prove things with induction. For now, though, we're simply going to use that lemma and use it to prove what we need to prove about bases. And that's often what lemmas are for. They're a little tool that we can help as a springboard, or use as a springboard for our more complicated proofs or more goal-oriented proofs. Here is the theorem we'd like to know. If V is a vector space and we have 2 bases, notice the subscript difference here. This one has P elements and this one has Q elements. So this is our counter-indication or nightmare scenario. What if I come up with a basis and you come up with a basis for the same space? Mine has 3 things in it, yours has 4 things in it. How can that work? Well, we're going to prove that we can't do that. Whenever I come up with a basis and you come up with a basis, they can be different vectors, but we're both going to have the same number in our sets when we're done. Just to put that into words, each of our bases for the same space, so each of our bases for V, must have the same number of elements. And that means that every basis for V is the same size. It's the same size. And again, a basis is a set of vectors, building blocks. And because of the way we define dimension, that the dimension of V is well defined. We're not going to get into an argument about how many vectors are in a basis because every basis has the same number of elements in it. And now we're going to actually write out the proof for this. The idea that 2 sets, which are both bases, are both going to have the same size, and it's going to turn out to be an application of the key lemma here done in 2 different ways. So the key lemma again says if I have a set that's linearly independent, it's going to have fewer or less than or equal to the number of elements in any spanning set. All right, so let's put that to work. Okay, so what do we know? We know set A up here is a basis. And what do we know about bases? Bases are sets which are 2 things. One, they are a generating set for V. basis for V. It'll be implied through this whole thing. We're always talking about the same vector space. It's a generating set for V, and 2 is a set that's linearly independent. Okay. So set A is a basis for V, which means that set A is linearly independent. Okay. Meanwhile, set B is a basis. Pardon me. Set B is a basis for V as well. And that means that set B, and the temptation is to say a linear, I actually don't want linear independence, I want two different things so I can use my key lemma, is a generating set. Is a generating set for V. Well, what do we know about the key lemma? Well, the key lemma says if set A is linearly independent, its number of elements, which is P, so P, size of A, size of set A, is going to be less than or equal to the size of the generating set. So generating set's Q here, so that's Q, and that's the size of set B. I hope you have some glimmer where this is going. Hey, I said set A was linearly independent, so the number of elements in it has to be smaller than set B, because set B is a generating set. But we don't have to put the A and B with that association. Both of these facts are true about both A and B, and so we can simply reverse this and get the same result the other way around. So, but also set A is a generating set, and set B is linearly independent, and so by the key lemma, did I say that here? I should say that's by the key lemma. Again, that states the relationship between the counts of any two sets that happen to be linearly independent and happen to be a generating set. And so we're going to apply the same thing here. Set A is generating set, set B is linearly independent. So A is the generating set this time, and it's going to be the larger size of that. Sorry, it's not A. The number of elements in there was, we called it P. And this time the linear independent set is Q. Again, this is the size of B. Set B, and this is the size of set A, and that again is by the key lemma. Well, there's only one way to have both of these be true. We have P less than or equal to Q, and Q is less than or equal to P. Therefore, P equals Q is the only option. And P and Q were the sizes of both bases. So the size of any two bases must be the same. And that is a fantastic result that gives us what we need to know about dimension. If we say a vector space has a basis, I find one, you find one, whatever we find in terms of the actual vectors, the number of elements in it must be the same.